In order to talk about dynamics, we first talk about acceleration, then we need to introduce some concept or review some physics about force, okay? Some people are more familiar with this, but let's start from the very basics. Let's say we have a rigid body. Okay, I have a rigid body. I have many forces applied to it. Okay, 3, maybe Fn. Okay, and each of them applied to the body. There's a point of application. The force applied to some point, it will contribute to the rotation or to the moment. So it's important. For example, this guy is like called P1, this P2, Okay, so overall I have so many forces, and then the net force this rigid body experience, you can think about them. And net force is just summation of all these individual forces. Okay, so the net force, the overall effect is just you sum all of these three vectors. F, let's call it F, is a summation of Fi. Okay, that's the overall force effect. And if I pick let's say, reference point, let's say this is my reference point O. Okay, then the force also generate a moment, and depending on what your reference point, your moment is, let's not have a coordinate, sorry. Let's say I want to find out the overall moment about a particular point O in the space. It could be on the body, it could be at other place, that's fine. So I want to know the total moment about this point O. Let's denote that by NO. What do you think about this NO? This is the moment. Okay, this is R3. You know individual moment, right? So moment in this case will be summation of I. Individual ones will be from O to Pi cross Fi. Each of the individual forces will generate some moment, right? And that vector from the reference point to the point of application of that force will give you R. R cross F will give you the moment or torque. Homeboy, is this okay?
Yeah, it's okay.
Okay. Now I'm going to ask questions. What about, I already know this, okay? I denote this as a range. Range is just putting this overall moment and overall force together in this way. And why we define this way, and it will be clear after maybe a few slides. But let's assume that this is range, and the force overall effect on the body consists of two parts. One is the sum of all the individual forces. The other one is the overall moment they generate about certain reference point. And the question would be, what if we change our reference point to, let's say, to Q. Okay, so I'm no longer interested in a moment about overall effect about O. I'm interested in another point, which is the Q. Let's say this is my Q. Okay, then by definition, NQ is nothing but summation of I, Q to Pi, this vector cross Fi. It's the same, all right? But I want to relate to my previous reference. Okay, so let's see how they're related. And this is nothing but if I say N of O, I want to keep this in mind, then plus summation I would say I need to add this term, I need to subtract this out. So we'll have Q Pi minus this guy, O Pi cross Fi. Hope you're fine with this. And then I will be this NO plus Pi got canceled out, right? Overall, you will have Q, I think this is, yes, Q to O cross F. Q to O cross summation, because this become PI is independent, subtract out this summation of Fi. So overall, this is NO plus QO cross F. Okay, so as if it's the net moment about O, then you think about the total force is applied to this point, then you find out the torque generated by this vector. Okay, so that's how it works. So if I know this, given me arbitrary reference point now, okay, I want to compute the moment for arbitrary point, I have this formula, and this formula also equal to, sometimes it's more convenient to write like F cross OQ. Okay, because A cross B equal to negative B cross A, and the vector I flip the sign, then I got this as well. So this is also true. Okay. I'm not sure whether you can recognize this. In this case, you remember that VQ equal to VO omega cross what? OQ, right? So that's exactly F played the role of omega, and NO plays the role of V of O. Okay, in this case, we can put them together. But we didn't put omega first, we put NO first. That's because of other things, because that will give me F transpose twist will give me power. Okay. Anyway, so that's the introduction for general overall effect about force or wrench. And let's call that wrench. The 6-dimensional thing is called wrench. Okay. So far the discussion so far is coordinate free. I hope you get used to the term. So far, I didn't say which coordinate system I talk about. It's mainly about pure physics. Then I gave a coordinate system. I can represent this wrench in different coordinate system. And similar to twist or special velocity, we often use the origin of the frame as the reference point to quantify the moment. Okay, for the force, it doesn't matter. It's a free vector, but for the moment, it matters where the point you are referring to. So we choose the origin of that frame. Now let's say, suppose that will be my definition of my range in A. Now suppose I have another range in B. Okay, that will be NOB in B and F in B. Okay, I want to know how F and FA, FB are related. So overall, I would say, let me draw the figure again. This is my rigid body. And initially I say I want to compute the range using reference frame O. Hold on, I call that A, maybe A. Later I say I want to represent this thing in B. Okay. I want to know how the same physical quantity relates to each other. First of all, let's look at this term. So what about FA and FB? What are their relation? Maybe Ruben.
Yeah. Okay.
Suppose my I have my TB in A, right? It's RBA and the PB in A. Okay. What is F? So
F
here the range is coordinate free. It does not have any coordinate yet. It only means all the vectors summed together is this F. And now I want to represent this F in A and B. What the relation between these two vectors?
It's the RBA.
Okay, because F is a free vector. It does not matter. There's no reference point thing. Okay, so it's just you use which basic vector to represent this free vector. Okay, I hope that's fine. Okay, that gave me my first relation. Now I need to worry about the moment. Okay, so let's say NOA, that's my moment about the point A. According, let's say this is a coordinate free, okay, coord free. I didn't say which, I just changed the reference point. Point is a physical quantity, okay? I say moment about the origin of A, OA, that's this guy, right? Equals to moment in OB, Liu Ben, plus what?
Plus the PAB cross F.
From, let's say, OA, OB, right?
Yeah.
Cross F. Cross FA or FB?
Let me see. Just
Cross
F.
F, right? That's a physical free vector. I haven't chosen a coordinate yet. It's just F, right? Okay. Okay, now I want to, this is what we got before. Then we want to use what? Yeah, let me pick, let's say choose frame, A frame to express this physics. What I got is the following. I will say NOA in A equal to NOB in A plus this is OA, OB, this vector in A cross F in A. And I want to relate to B, so I will say this guy is R, because now it's R BA times NOB in B. Okay, plus this cross this, right? So I can, how to say? This one is negative OA in A, right? So I will let me just skip one tiny step. This is RBA times negative PAB. The point A in B, that's this vector. How to say? Yeah, in B and RBA. Okay, and the cross FB. I'm not sure whether I lose anyone or not. So overall, you got, if you multiply this out, what you got? You got PA in A, right? And this guy is what? Negative PA in A, right? Because PA in A would be, no, sorry. I think it's this vector is from A to B, let's see. From A to B, that's point A in B, and times negative. That's the vector, and then times this one will get this. Okay, I think it's right. And then this one, it will be RB in A times NOB in B, negative, and RBA, skew symmetric PA in B times F in B. Okay, so I have this relation, this guy. Overall, I have this, the first relation, this is my second relation, and the first plus second will implies the following, implies in matrix form NOA in A and FA equals, this will be RBA. This is RBA again. This is zero matrix. And this will be this part, which is negative RBA and PAB and times NOB in B and F in B. Okay, so that's, I don't have space. I think I need one more space. hold on. Okay, overall, this guy, I will denote this guy, as denoted as x, change of coordinate b to a. But it's different from our twist change of coordinate. I'll call it star. Okay, and you can easily check xba star equal to xab transpose. You remember xab is RAB0 RAB and RAB, sorry, this is a PAB, skew symmetric times RAB, right? That's the adjoint that Fusen-Wolf was very familiar with, right? And if you take transpose, RAB becomes RBA, right? And this RBA and the skew symmetric take transpose, there's a negative sign. So that's why it equals to this guy. All right. So I think it's about time. And we'll finish introducing spatial acceleration and spatial force, which is wrench. So next time we will finish rigid body dynamics. Okay, let's continue. Let's continue our discussion. Let's see that. Let's continue our discussion from last time. I think last time we finished introducing the spatial force, which is wrench. Okay, is this here? Oh, here. Oh, yes. There's one question that Fusen asked. I think it's why that from this step to step why this equation holds. Let me explain. Well, there's algebraic ways to explain that. I think some student in the chat area just already mentioned that. But for me, this equation is I tend to think in a coordinate free way. So for example, to me, I don't want algebraic formulas. And for example, this means this equals to OA, OB hat cross F expressed in A, right? That's what we're trying to do. And I can write it in this way. So this is the vector expressed in A. I would say this is B, A, OA, OB vector cross F. This is expressed in B. So that's where I got this part. So I don't need to use the formula, just from coordinate free way. It's just we want to find the vector, right? And we want to find the vector in B, then we did a change of coordinate to A. That's how I think. But of course, you can apply formulas so that it also works. Fusen, does this make sense to you now?
Yes.
Okay. All right. So last time I think we finished introducing this range, and also derived in the range the change of coordinate for range is this x from B to A star, and the expression or the formula for this change of coordinate matrix, this is 6x6 matrix, just like a change of coordinate for twist, and with the star is just it's BA star equal to AB XAB take transpose. Okay, that's a property you need to be aware of. Okay, with that, let's start talking about more kind of results related to spatial range and spatial force and range. First of all, I want to mention some kind of invariant property, which is power. Okay, I want to recall the fact that if you have a point mass, so you have a point mass, it's moving with certain velocity, and you apply a force. Okay, and how much work this force has done to this point really depends on the angle between the force and the velocity, right? So that's a basic high school physics, and roughly the power equals to You need to do projection better, right? So the power equal to F transpose times V. In other words, is the inner product between F and the velocity. Okay, so this gives us the formula for the power or the instantaneous work done by the force. This relation can also be generalized to spatial force. Okay? It's basically we lump together the power done by the force and also the rotational power, which is the power done by the torque. Okay, so in general, if we have a twist or spatial velocity, it has two components, right? It's a omega and also linear velocity, and also a wrench. So X on the body, the power is nothing but also the inner product, the 6-dimensional vector inner product between the spatial force and the spatial velocity. Okay, this is also equal to FA inner product transpose times VA. Okay, this guy is a scalar. So no matter what coordinate you use to express force or twist, it doesn't matter, right? And eventually you get a scalar is a coordinate free, okay, independent of reference frames. If you want to write this out, if you like, this is a, let's say this is 6x1 vector, take transpose, right? This is also 6x1, so you can take inner product. Okay, if you write every component out, not every component out, but the rotation and the linear velocity part separately, if you write them separately, then you have omega A transpose, and this is times that, right? This is the moment OA in A plus VOA in A transpose times FA, okay? This is the linear power, this is the rotational power, okay? This is the rotational power. Okay, that's just one notation convenience. You take so the inner product between spatial wrench and the twist give you a power, and the power is coordinate independent. Okay, frame independent. All right. Another thing I want to mention is the joint torque. Okay, this term mathematically sometimes it's a little bit less rigorous. It's just like when you say force, I'm not sure what appears in your mind. It should be a vector, but some people think force is a scalar, right? If the direction is clear from the context, force is also just meaning the magnitude along that direction. And joint torque, when joint is completely specified, its rotational axis is almost fixed. Okay, so people often use this torque is different from the scalar torque. Okay, so it's a joint torque. Let's see how we can rigorously argue through that. So suppose we have a joint. Let's say this is our joint, and this is our link or body, and it has a velocity. Okay, this is a twist or spatial velocity. Let's say suppose, I mean, because this joint connect with the body, so there must be a force the joint applies to the body. Okay, and because the rigid body, the velocity of this body is mainly due to the joint motion. Okay, so by our kind of screw axis representation, this velocity is just screw axis times the joint dot. Okay, the theta dot. I think we have seen this many times. So let F be the wrench provided by the joint, and then the power produced by the joint is given by it's this, right? So its power is the inner product between this, and we substitute this spatial velocity. You get actually you got this, right? You got the screw axis times the speed you rotate about the screw axis. Okay, that's the power, and the inner product with the wrench, that's the power. But this guy is a scalar, right? So this is a scalar, so you can move it out. So eventually you get this term. Okay, so we can define, okay, more rigorously. You can define this guy as let's define it as tau, okay, which is maybe Liu Ben, are you there?
Yeah.
Okay, so is this tau here is a scalar or vector? What's its dimension?
Here is a scalar.
Okay, it's a scalar. Okay, it roughly represents the projection of the force onto the screw axis. Okay, and we call this guy a torque. It's not a torque. Well, sometimes people say moment also is a torque. I mean, they're interchangeable terminologies, but this torque is really the joint torque. Okay, so we define this as the projection of the wrench onto the screw axis. You can think about this as the effective part of that wrench to generate the joint motion. Because other wrench, the joint may substitute, may kind of I think the joint may somehow generate force, not only kind of generate motion, but also counteract other things. Okay, so this part is only the force or wrench that projected onto the screw axis. That's really kind of generate the motion along the screw axis. Okay, there may be other reaction force that doesn't really contribute to the motion. So that's not considered here. So this guy is a scalar, is a joint torque. Okay, let's call that joint torque. This, when I say joint torque, you can think, okay, it's just it's a scalar variable now, all right? Because the axis, everything else, the directional things has been really kind of completely specified. So so this become a scalar thing for each joint. Okay, if you have a torque vector, then it becomes every joint. There's multiple joint, you have a joint vector. Each joint, this is a scalar. Okay, sometimes it's also called generalized force using general coordinates. Sometimes the coordinates called Q, right? Tau is a generalized force. Okay, so the torque times the speed of the rotation about the screw axis or the joint variables derivative, theta dot, will give you the power of that particular joint, the instantaneous work done of the joint motor provided to the body. Okay, so that's some kind of clarification of the terminology. Now let's move on to the next important topic, which is the spatial momentum. Okay, I think some student, I'm not sure your background, often do not have a solid understanding of this inertia matrix, even moment or momentum. And so I will just try to start from a little bit more kind of basics, okay? Let's think about a very, very basic case. Let's start from the point mass. That's a building block to understand the rigid body. Because rigid body is a lot of those point mass made up of all of these point mass. Okay, let's think about a point mass with the mass with m. Okay, let's think about this in a frame. This is our frame, and suppose it rotate about this omega, this axis, this rotation. Let's think about this this point mass here. Let's use another color. This guy is here. Okay, it's rotate about that axis, right? So you will have a rotation motion, and it also has a linear velocity. Let's say this is v. Okay, and I could apply a force to this point mass, right? Will change its motion. Okay, so that will be our, let's call that force may be different direction, that may be like this, right? And we also have a position vector, which is another vector, which is from the origin to that particular point. Let's say that's the denote the location of that point at the current time. Let's call that R. Okay, so let's recall some maybe high school physics. So the velocity is the change or speed, the change of the derivative of the position, right? So V equal to R dot. Okay, we have no problem with that. And A equal to V dot, which is R double dot. right? And we are considering in R3, although we consider point mass, we are not in the plane, but we're considering R3 in general. Okay, that's the velocity. When you think about the rotational world, let's think about this as a linear velocity, linear motion. This part is rotational world. Okay. This corresponds to the following. So omega, you can also think about this motion also has omega, right? Omega, if we represent omega, it's a direction, the rotation axis, let's call it head. Rotation axis times theta dot. Okay, there's a theta dot, it rotates about that axis. And the linear motion due to this rotation, and it's omega cross r. Well, I think that's correct. And then in the linear motion world, is a force, and the force equal to what? Ma, right? That's Newton's second law. And this is mv dot is r double dot. Okay. And this guy correspond to force, correspond to here moment or torque. And the moment, using our current notation, somehow adopt the Roy-Featherstone's notation, so it's a little bit ugly. So which is the n, it's not natural number. The moment is n, it equals r cross f. So from this f to this here, generate the moment. And then we talk about momentum, okay? Linear momentum. Ruben, what is momentum?
Moment is the physics
It is physics, yes.
yeah.
Uh-huh.
It's like the force corresponding to the linear velocity and the linear the momentum equals to I know L equals to R cross the
I use a wrong bad notation, but anyway, linear momentum. What is the linear momentum?
Linear momentum is the translation vector across the
That's rotational momentum.
Yeah, that's linear. Linear momentum is the mass times v.
Okay, great. I call it L, but typically L means, maybe I confuse you with the notation. Typically in physics, L means rotational momentum. Linear momentum, they use P. But somehow let's use it here, okay? In our kind of graduate class, we're not bothered that much with those conventional notation. Let's just use L for linear momentum. And for angular momentum, let's say for angular, it is, let's call that phi, okay? This is R, that's what Leuben was trying to say, I thought. It's R cross the linear momentum, okay? And momentum physically means how hard the things can be changed, the motion can be changed, right? If you want to change the momentum, you need to apply a force. Otherwise, the momentum is conserved, right? And rotational momentum, the same thing, how hard to stop the spinning, stop or slow down the rotation or change the rotation motion, okay? And if you want to change it, you have to apply a torque. Okay, that's what it means. What I want to dive into a little bit more details is here. Here is the point mass, and this is the angular momentum, and R cross L. Let's substitute L. That's R cross L is what? mv, right? V velocity due to this rotation, it is what? It is omega cross R. Are you with me? Agree? Okay. And we also know this guy, m is a scalar. It's a mass. We can put it out. So m times this will be r cross omega cross r. Okay. Well, that's what it is. And but I want to move omega out. So how we should do? So we can do it by, because a cross b equal to negative b cross a, right? That's the fact. So I can change the order. So it becomes m times r cross omega. Okay. And we know that each of these cross, we can use a matrix interpretation. That will be my skew symmetric matrix, R bracket times, oh, sorry, I think there's a negative sign here, right? So this is a negative R, let's call it negative R. And negative R times omega, because I somehow use a matrix interpretation so that I don't need to use this cross. And so this will be a scalar times a skew-symmetric matrix and times another skew-symmetric matrix, which is also related to R. Okay. So overall, maybe Liu Ben again, what's the dimension of this guy?
The dimension of this guy is 3 by 3.
Yeah, this is a 3 by 3 matrix. And this matrix is the inertia matrix of this point math. Okay, with reference to this origin. Okay, so that becomes the inertia, rotational inertia matrix already. Okay, we derive it for a point math. I hope you see what I mean, right? So this is the inertia matrix for this point math. Okay, for this point mass, expressed about that O point. Okay, it's really depend on how you choose your reference frame. Okay, so we typically use identity. Okay, sorry, not identity. This I to denote this inertia matrix. Okay, so point mass also has a inertia matrix in R3. That's what I want to emphasize. Okay. So now let's think about, in general, how to do that for rotational inertia. Okay. Typically, I don't discuss this. I think maybe Hongbo is there? Okay. So can you explain this formula, or how do you understand this inertia definition formula? This is a definition, by the way.
I think
did you remember this, or what? Have you learned this before?
Yeah. So if we take each part of a rigid body, like a point, and we can calculate the inertia of its point, then we do the
okay.
increment to this all points.
Great. Suppose there's a rigid body. Okay, we divide it. I mean, that's the foundation for calculus, right? They divide it into infinitesimal small cubicles, and it's small size, and each of them is mass I. Okay, and each of them will have an inertia matrix, right? The bottom line is following. Okay, so if you only consider rotation motion, all of those points have the same angular velocity. So omega doesn't change, right? Because that's why. Because omega is like a parameterization for representing the rotation velocity. All the points, the linear velocity is omega cross that point's position. And omega is the same for all these things on the body. And so overall, I can say my, I can also derive it, by the way. So I can say this is a phi. This is my overall body angular momentum. will be summation of mi times individual of this, right? So it's basically here, okay, mi times ri times ri negative times omega. Since omega doesn't change, so overall I will have this. I call this my inertia matrix for the whole body. And if you do the division, if you divide it into very infinitesimal volumes, and then it becomes this. Okay, this guy is the density, right? The density function. If you take this and divide it by the volume, that becomes the density function. And why it has a transpose here? Because this is also equal to Ri transpose, right? It's a skew symmetric. Either way is fine. And times dr is the volume. Okay, I think it's a dv. Okay, and anyway, so volume integration. I hope that's clean. If you don't like calculus, just think about the summation of individual point mass. That's fine. And so this guy, the point is that this matrix depends on coordinate system. Coordinate system, sorry, to represent R, okay, Ri. So depending on what coordinate system you use to represent this point position, you have different vectors, right? If you have different coordinate system, you have even different vectors. And also the vector need to express in that coordinate system. So the coordinate will be different. So the rotation or the inertia matrix becomes, it's not like a constant matrix by default. It's actually it's a coordinate system dependent. Okay, and and typically we would like to express those inertia matrix using the body frame. Okay, the frame moves with the body, and ideally will be central mass. So so if the origin coincides with the central mass, then so this matrix doesn't change over time. Okay, otherwise you don't have to be co-located with the central mass. As long as it's related to a frame that fixed to the body, is fine. Okay, it will be constant. If the frame is the inertia frame, then the body is moving, then this inertia matrix will also be time dependent. Okay, so but I would like to ask you, I'm not sure whether you even thought about this before. What's the definition? What's the formal definition for COM? Hongbo, how do you define COM?
I think we add
Let's see, X COM,
R times
okay?
M together.
Okay, center mass is well, is divided by the total mass, and this is my density times R times dV. Okay, that's a formal definition for center mass. Okay, so weighted sum of all these positions. Its position, how much is weight, depend on how dense the mass is around that local area. Or you can think about this as or maybe you like let's say C is also summation of mi. If you like those kind of infinitesimal way of thinking, that's mi Ri. Okay, it's weighted sum of all the point locations, and its weight is the infinitesimal mass around that location. Okay, that's the central mass. Oh, sorry. You need to divide by the average, right? Divide by 1 over m. Okay, so but based on this definition, if I choose my coordinate system to be the origin of the coordinate system to be at the central mass, then what we can get the following. So we can have let's say if how to say that? Let me put it this way, okay? So let's say if C is COM, then let's say you're using this kind of more intuitive. This is let's say MI times, let's say from the origin to Ri, that will be my vector to represent the location, right? This vector times this weight equal to 0. Okay, actually you can define C as the point makes this thing equal to 0, right? In general, that means summation of I, MI, Ri. Let's just say that CRI, that's a vector, right? Equal to 0. And one consequence of this that often useful is summation of MI times this vector sum to 0. Actually, this can be easily proved, okay? So the skew symmetric matrix of this vector, you know, so this is the R3 vector. It will generate a skew symmetric matrix. This equal to 0. Okay. So because well, this is a linear operation, so this can be easily verified. Okay. Any questions? Fuzhen. Let's keep this in mind, and also keep this in mind. If C is the center of mass, okay. If C is not center of mass, it doesn't hold, right? Okay. So with this preparation, let's define spatial momentum. Okay, a lot of textbook or any discussion, they don't give those baby steps to set up the context for you to truly understand what's going on. And I'm talking a little bit slow here, just trying to make sure everyone have from the very, very fundamental to know why the formula holds. Okay, so let's say that first of all, linear momentum. Maybe Liu Ben, what is the linear momentum here? Suppose I have a body, okay? And I know here maybe the central mass, okay? I know the central mass velocity is VC.
The linear momentum is the total mass m times VC.
This linear momentum is m times VC, okay? This VC is a little bit confusing for, I think misleading. I would rather say this center of mass. It doesn't matter what coordinate you use to represent this velocity, okay? Because this VC is a twist here. Here we said it's a frame is collocated at the center of mass, but doesn't matter. It's actually just linear momentum is just about this. It has to be a velocity, the velocity of the center of mass point, okay? So this doesn't change. If I say this way, so that this twist has a frame that whose origin is the center of mass, then this is a VC. Okay, this is a VC. Okay. Why is this? Can you prove this, Liu Ben? Nobody asked this question before, maybe. So this linear momentum of the body, and the body consists of all of these small particles, right? So this is summation of I of this linear momentum of its motion, its individual kind of box here, right? Okay, let's think them as together. Because it is a body, so this guy is equal to this mi times. You can represent or parameterize all the, because the body has an infinite number of points, right? You can parameterize all the velocity of all these points with some reference. For example, this here is reference VC, right? VC plus omega cross from C to Ri. This vector, that's our twist by definition, we have this, right? Twist is the penetration of the whole body's velocities. And if you get that, then this becomes summation I, mi, vc, and here vc is independent of the location of the mass, so here you can write it like this, right? And plus summation mi, and if I do a AB equal to negative BA, so then I'll say this is a CRI cross omega, right? Cross negative omega, let's say that. Typically, I would say negative CRI, that would be better. Let's say this is omega, this is negative CRI. Okay, so here, this guy is 0, equal to omega I, mi. Let's say negative sign here is it's a skew symmetric matrix, CRI here, and this is 0. Okay, so overall, I will have, this is MVC. That's why we have rigid body can be represented by the total mass times the center of mass velocity. Okay, if it's not center of mass, here is non-zero. Okay, so the definition of linear momentum is really about mass times the velocity of the center of mass. Okay. All right, that's the first part. Now, second part, which is the angular momentum about COM. All right, angular momentum. Now again, this rigid body has infinite number of points or small kind of a mass, point mass. Made up of so many different small point mass. Then I would say angular momentum about central mass. That means you use central mass as a reference point. This equals to Liu Ben, what is it? Oh, we derived it, right? We derived this already, right? So now I can say it is equal to I call this I bar about center mass times omega, and this guy was defined as this, okay? I bar about center mass. That means I use center mass as the origin of some frame. I didn't say the orientation of that frame. Is the origin of that frame really matters a lot here, okay? Any question about this? Or you can, how to say? If you want, you can prove this. I'm not sure whether you're interested or not, but I want to prove everything for you. At least I want you to encourage you to think what's really happening. Okay, so in general, phi of C equal to from summation of all the particles and the location from the C to that R, that's the vector. Okay, as I mentioned before, this formula, this R is a vector from origin or the reference point to the position of that of your point mass position. Okay, that's the vector. If you change your reference point, the vector also changes, right? Here I have C because I about central mass, so from central mass to R, that's my vector, cross linear momentum of that particular point mass, which is MVI. Okay, and so this will equal to summation of Ri, so it's also CRI cross, because, well, I use this formula again, all right, so that will be my MIVC, okay, and plus MI omega cross CRI vector, okay. Overall, I have summation I CRI cross MI and times whole thing times VC, right? Plus here this part, okay. So it will be I move MI here, so that will become CRI cross omega cross CRI thing. And by our previous discussion, this guy will be 0. AB equal to negative BA, so it's still MI. Sorry, I don't think that's like I can well, MI is a scalar, so well, if I want to keep the cross, then that's better to have MI VC here. Okay, you can move it to the MI can go out, go here, right? So overall, you still have a 0. Okay, and here this part is nothing but A equal to IC times omega, right? Omega can go out, and IC is the inertia matrix defined as the integral or summation of all these individual point mass inertias. Inertia matrix. Okay, that's the how we can really kind of from the baby point mass to go to get everything you need for the rigid body angular momentum. And the key now comes from that, what about I change a reference point? Okay, if I change a reference point, that's my previous I at central mass. Now the inertia becomes, I would say, by definition, it's still, you can say, summation of I. This is ORI now. Your reference point changed from O to C, from C to O, cross, and this MI VI, that's my linear momentum of each particles. Okay, and maybe that will give you a homework. I don't want to go through these steps. Just exactly follow similar steps. You'll find out. Of course, you need to introduce some intermediate variables. You find out this equal to O phi of C, okay, plus OC vector cross LC, the L, okay, the linear momentum part, okay. This is the linear momentum of the body, okay. So let's keep this in mind. Let me just summarize it as separate formula. So if you change that O, then the VC plus OC cross times linear momentum. But graphically, you can view this figure. You can find it. The notation is different from my kind of notation here. This is my linear momentum. This is my angular momentum. Okay, but roughly you can see graphically it makes sense, right? It's almost like there's a linear momentum here, and you need to times this R here. But anyway, so from baby steps, you can also derive this formula, and let's keep this in mind. Okay, so overall, I have a spatial momentum. Let's define the spatial momentum as H, and it consists of two parts. It's angular momentum and the linear momentum. So this becomes R6, a vector. Okay, so here is the angular momentum is also a vector. Okay, it's not completely aligned with the rotational axis. It's actually times the inertial matrix, you become maybe another vector, but it's in R3. And linear momentum is in the same direction as the central mass velocity. Okay, so overall you have this spatial momentum. Just lump together this rotational and the linear momentum. Any questions so far? I will say this part is your homework, okay? You can check, right? So now let's think about how to represent this guy. The formula here I gave is almost like a coordinate free. Okay, I didn't say which coordinate I use to express those vectors. All I care about is a reference point. It's just like when we define twist. Okay, so what are the reference point you want to express all the other particles' velocity as the velocities of that point? Okay, here is the same. I didn't say which coordinate system we have to use, but we just need to make sure that there's a reference point specified. If you change reference point, then only this part changes, but IO doesn't change. Okay, IO doesn't depend on reference point. It's only the center mass velocity is fixed. Okay, if it is not center mass, then this part won't be 0. I hope the derivation can help you further understand this concept. Okay, let's see how we can express this 60 vector in different frames. And suppose I have, let's say I have 2 frames, right? I have A frame as my frame. I have a maybe central mass frame, C, okay? So I will express this momentum initially at L in C. Sorry, this is first is the angular. So this is a phi about C in C. Okay. Let me be more clear. That will be origin of C frame in C and L in C. Okay, I don't write anything here because L doesn't depend on reference point. I hope that's clear. This is H in A. Maybe I can test your understanding, Liu Ben. What would be my notation here? Phi of what, L of what? Okay.
Yeah. Phi O no.
No.
Let me see.
Hongbo.
Phi
Liu Ben, you can continue. Sorry.
Phi OCA.
Phi O what? OCA? There's
OA.
OA. Okay.
A. OA.
Expressed in
frame A.
Okay. What about here? L.
L no subscript.
Okay.
And express in A.
Okay. All right. Great. Think about coordinate free first, and then choose a frame to represent the vector. Okay, that's if you got confused, you always need to separate physical insight from the those tedious coordinate details. Okay, that's the way you can stay kind of cool in this kind of heavy notation, right? Okay, now I want to know how these 2 coordinates relate to each other. Okay, so first of all, maybe Hongbo, what is let's say what LA? What is the relation of LA and LC? Suppose I have whatever that I have this change of coordinate. This is my T CA equal to RCA and PCA. Okay. Hongbo, you there?
I'm here.
You muted.
Oh yeah, I'm here.
Oh, what's the relation you think?
Well, I think it's RCA.
Do we have other things plus anything?
Yeah, let me think. Well,
No, it doesn't, right?
Uh,
As I mentioned, this guy does not matter where the origin is. It's only a vector. It just represents a center of mass in different coordinate frame because that velocity, sorry, center of mass velocity, and that center of mass velocity is a free vector. It's a velocity vector. Okay, so that's fine. So anything has, if you don't have a substitute here, a subscript here, it's just a free vector. Okay, it doesn't matter which the origin of the frame, where the origin of the frame is. In other words, this guy is 3/1. This guy is 3/1. Of course, the change of coordinate for orientation is that. So this is nothing but what? Let's say I have a central mass. That's my vector, right? It's a vector. It doesn't really matter where my coordinate frame is. It's a vector in the space. It's like a, It's like this vector in the space, and I can represent it in A or in C. I think all of you will agree, hopefully, that will, let's see, is RCA. But this is okay?
yes, okay.
Okay, so then L is nothing but the scalar times this, so it's the same. By definition, it's the same, okay? So let's erase this part. Okay, let me finish this part before having the break. Another one is phi of A. That's my, well, that depends on the reference point now. Okay, that's the angular momentum about, and when I choose the frame, I will choose the reference point to collocate it with the origin of that frame. So then I need to say phi of OA in A. How does that relate to phi of OC in C, right? That's what my purpose, but let's do coordinate free think first, okay? Let's say coordinate free. So phi of A, let's say not A, sorry, O of A, that means the angular momentum of the body above a reference point OA. I just pick OA. It has nothing to do with how I represent this vector. I just pick OA as a reference point. Then I know this relate to OC reference point plus from OA to OC. That's our formula I want you to know. That's coordinate free formula. So from OA to OC cross linear velocity. Sorry, linear momentum, right? You agree? Then I can use coordinate. Okay, I can now express this in coordinate using A frame coordinate. Let's say that. So then the phi of OA in A equal to here, this guy will be phi of OC. I can do that. So I can from C to A, phi of OC in C times this will give me this guy in A, right? Plus whole thing in A, but I can do that because I want to have this same factor here. So I will say RCA times the whole thing expressed in C, which is actually negative PAC cross LC. Okay. So this is nothing but the these from C to OC to OA. So that's where there's a negative sign. Actually, if you do some kind of check, you find out these two relations already. That's one thing. This is, if you want to write it like a matrix vector form, that will be RCA. What else? RCA. Here is RCA as well. Let me think. This row, this is the second row, sorry. This is just one row. So that will be my RCA times that's OC, VOCC, IOC. This becomes RCA, negative PCA, skew symmetric. All right. I have this at the second row, the first row. So overall, let me skip that step. Overall, I would say H in A actually equal to from C to A star. The change of coordinate for force matrix that has exactly the same expression, and for the change of coordinate for the momentum. So this is H in C. Okay. So in other words, the momentum actually spatial momentum behaves same way as force. So this is R6. This is in R6, right? So this 6 dimensional vector actually lies in the space that's similar or the same as the force space or wrench space, not the same as the twist space. Okay, you can check this, and overall, let's remember that momentum is almost like, you can think about it as force, because change of momentum is just force. Okay, so behave this like that. Well, let's take a break. All right, let's come back to that discussion. Let's start talking about inertia. We introduced the inertia matrix, the rotational inertia matrix. That's typically any physics or undergraduate robotic class, they will talk about inertia matrix. In this class, since we talk about twist and the spatial velocity and the spatial force and the spatial momentum, and we can generalize the rotational inertia to a spatial inertia. Just need to put two things together. Okay, I want you to think about. You don't have to. Okay, you can think about this as you think about inertia matrix. Inertia is a matrix. Okay, in our case, it can be called tensor, but let's just think about that as a matrix. Think about this matrix as a mapping that maps from velocity to force space. Okay, think about let's see, think about inertia. Let me see, how do I write this part? Think about inertia matrix as mapping from the motion space M to force space F. Okay, I didn't introduce this to space, but this is where the twist resides. This is twist and spatial acceleration. Let's say this is a V or acceleration, and this guy is almost like a wrench and momentum. They live in that kind of space. So inertia is actually mapping from velocity to force or momentum, or to the force space at least. Okay, it's a linear mapping. So, so momentum equal to the linear mapping that times this velocity becomes momentum. That's a coordinate-free way of thinking. And this is a 6x6 matrix. This is a 6x1 vector. Twist is also 6x1 vector, right? And in the simplest case to represent this spatial inertia matrix is when the frame coincides with central mass. Okay, so let's think about this special case, all right? Let's think about, let C be a frame whose origin coincides with central mass. In this case, we know, okay, maybe answer that Fuzhen's question as well. In this case, we know, let's suppose this is my twist, right? Twist in C equal to omega in C and VC in C, okay? So in this case, we know this is my notation, and also V of center of mass in C is just VC in C, okay? Because this frame is rigidly attached to the body, and they are the same. That's why L in C is M times VC in C. Well, then that's okay?
Yes.
Okay, so this is the key, okay? Anyway, by definition, L is really M times central mass, okay? But here, because these are the same, so that's why you have this relation. In other frame, this may not be true, okay? And also, because of this, I know rotational inertia about this in C equals to I call it bar. It's constant matrix about central mass, and express that in C. That means think about rotation inertia matrix. It's the weighted sum of Ri skew symmetric type negative Ri skew symmetric matrix. The Ri is a location vector of that particular point mass, and you want to represent that vector in C. And you also depend on where the origin is, right? So in this case, both the origin and the orientation of the frame matters. Okay. So in this case, this guy equal to this omega, and also in C. Okay. So overall, you will say H in C equals to, in this case, here this is IC bar C. This is a 3x3 matrix. There's a formula for this, and omega in C. And also here is M times VC in C. And this equals to IC bar C and 0, 0. M is a scalar times I 3x3. I use I 3x3 denotes a, well, its notation is a little bit bad, but it's a identity matrix, right? That's a 3x3 identity matrix, not inertia matrix. Identity matrix. Okay. Times my twist, all right, which is my, let's just directly write down the twist, times V of C. So in this special case, when I choose a frame C and this C coincides with the origin coincides with central mass, then I can have this structure. If it is not the case, then I may not have this structure because it may not be diagonal. But we always start with this case, then we do change of coordinate for H and also for this spatial identity matrix. Okay, so overall we have this is our so-called script IC. So for my handwriting, it's hard to tell, but for the typewritten case, it's a little bit clear. Okay, this is my identity matrix, 3x3 identity matrix. Okay, so that's the so-called, this is a 6x6 matrix. It's so-called spatial inertia matrix. I think that's a typo, spatial inertia matrix. All right, so we know how to represent it in the very simple way where you have diagonal matrix, but we can also express the inertia matrix in arbitrary frame. The orientation and origin can move arbitrarily, and this can be derived. Okay, it can be derived by the change of coordinate for H. For example, we have H. Suppose let's say H of A equal to inertia, spatial inertia in A times V of A. Suppose that's our goal, right? Inertia matrix maps the, so regardless our coordinate free way, we want to use different frames to represent this physics. And in A frame, that's this. In B or C frame, that will be the same formula. It's just expressed in C. Okay, I want to relate that into C. Then I can write this like, we know the change of coordinate for H, right? So that will be from C to A star times H of C. Okay, and then XC of to A star times H of C, which is, let me think, H will be IC, spatial inertia matrix in C frame, times twist in C. Right? And then I also want to change back, let's say, CA star IC times, if I want to factor this out, so I'll have a change of coordinate for twist, which is C to A to C. Okay, this is A to C times V of A, right? Overall, you have this equality, all the equality holds, right? So overall, you have IA times VA equal to this guy times VA. So overall, these two guys are the same, okay? So that's why you have this formula. Okay. So again, if you want to think about inertia matrix as a mapping from velocity to force space, okay, this makes sense, right? So you say you want to represent this mapping in C or in A. If I say I know how to do this mapping in C, then I want to know how to do this mapping if I choose coordinate in A, then I need to, well, from motion space to force space, right? I need to, then in the motion space, I need to change coordinate using twist change of coordinate from A to C first. Then you apply the motion, apply the operator, apply the mapping in C, and then change back to A, but this change back is in the force space. So that's why you have a star here. Okay, so that's how I can see this formula, but if you want to memorize it, that's fine, but I never memorize anything. Okay, any questions? All right, a very important special case is the following. It's a special case is when that is when A has same orientation of this central mass frame. Okay, central mass frame, the key is that it's located at the center of mass. Okay, the orientation of that frame doesn't matter that much, but you just need to fix one, right? And then you compute, then you need to compute this bar in C, right? As long as you fix central mass, this guy is fixed. You fix central mass frame, this guy is fixed. This is a constant matrix. And if you keep the orientation the same, but you move the origin of the frame away, that's your A frame. For example, let's say this is my central mass frame here, okay? Then this is my O of C, right? Just central mass, sorry. Let's say C, central mass. Then if you have the same orientation, let's say this is my A frame, same orientation, but location of this origin are different, then I can write my inertial frame. Sorry, I can write my spatial inertial matrix explicitly. Okay, so in this case, we know x c to a equal to this change of coordinate for twist. Actually, in this case, because the orientation are the same, so the RCA is identity. So I have identity 0 identity. Here is PCA skew symmetric. That's my matrix. And using this guy, you can apply this formula. You got this IA in a very special form that I think everyone need to know it at least. When you use Drake, actually, you can see this formula in the document. M, this is a PCA skew symmetric, and the PCA transpose. Here is M, PCA. Here is M, PCA skew symmetric, and M times R 3/3 matrix. So this becomes more ugly. It's not like in this central mass frame, this diagonal. It becomes different here, but it's still oftentimes, maybe we will do a Drake example next time. You may select your origin of the frame to express the inertial matrix at a frame whose origin is away from central mass. Okay, then you need to know how to compute its inertial matrix. Okay, so this is an important result. You don't need to memorize, but you need to know, be aware of it. Okay, so let's finally, let's talk about, we have introduced almost everything for synchronous body dynamics. We have done spatial acceleration, that's derivative of the twist, and the spatial force, which is wrench, and spatial momentum, okay, and the mapping between velocity to momentum, which is the inertial matrix. All of them are 6D or 6x6 matrices now. Okay, one thing I have to, I don't want to discuss in detail, but I have to mention is that you often need to work with moving frames. Okay, just like we spend a lot of time to discuss why you have spatial cross product, just try to introduce it to handle moving frames, okay? We can briefly recall that, or we can briefly discuss that here for forces, okay? So if you fix, let me use more space from here maybe. Suppose if you have a force, you have a frame, let's call it frame B. Okay, I can say a wrench it's a vector in the 6D vector in forces, and if I give a coordinate in B, what I really mean is that a linear combination of the force basis vectors, okay, which is let's call the EB1 star. Okay, let's use star to denote some kind of most force space, EB2 star, all the way to EB6 star times F in B. Okay, these are numbers. Okay, typically these are 1, 2, 3, something like that. Okay, these numbers really means the linear combination coefficient, and each of this is a physical vector. Okay, this is each of this. Okay, it's a force space basis vector. Before I mentioned that there's a motion basis vector, right? It means means a vector field, or means a motion that rotate about the xb axis. And here's the same. It's really this basis vector really represents the physical quantity, which is here maybe the elementary. We can think about the elementary forces or torque or moment. Okay. For example, this guy really means, if you see this guy, this is a physical quantity, represent a unit moment, okay, torque around this, from here, around this axis, okay? So if, I don't want to go to too much detail because we spend a lot of time for the motion part, okay? So if I do a derivative, of this force, then I do what? Then I, let me call this guy, this matrix, let's call that XB star. I didn't have any, so this guy doesn't mean anything, okay? B is the basis of the B frame, force vector in the B frame. And I didn't say I express this in O or in A, it doesn't matter. It's just, this is really kind of physical vectors there. It's elementary force vectors representing elementary forces or torques. Okay, so in this way, if you based on this formula, you get F dot equal to XB star dot times FB plus FB star times FB whole thing dot, right? We use our notation. This is FB ring, which is apparent derivative of the coordinate, okay? And this guy is really tells you how fast your coordinate, your basis vector moves, okay? So if, so this is basically a review almost for previous case, but now we just need to handle this case. It turns out, okay, it turns out you can derive it. If you're really familiar with physics, you can even think about it in mind. You can write down the formula. But it turns out it can be shown, or it turns out if B frame, so this is the frame. Frame is a rigid body, right? If B frame has velocity, let's say V of B. I didn't say which frame I represent this velocity. This is the velocity of that frame. Okay, if that's the case, then we know. Let me write down here. Then X dot. Okay. Let me think this way. Okay. Let me do by all the basis vectors. So then, let's say EBI star dot. That's the vector in this matrix, okay? The basis vector, okay, of the force expressed in B. Then this dot, this physical change. This vector change over time because of the motion change over time. And sorry, because B change over time. So this guy actually equal to V of B, because I know the frame has a rigid body motion cross star EBI star. While there's a shorthand notation, I didn't define what this means, okay? So this guy becomes, it's similar to the spatial cross product. It just have a star now. It's a spatial cross product for forces. Okay, so overall I will have, so by definition, this let's call that by definition. So where, let's say where this cross star defined as the following. Suppose I have V is a vector, let's call that omega V, and F is another vector, which is N and a small f. So this V cross star F is defined as omega cross N, this cross this, plus V cross F, and below is omega cross F. Okay, that's the definition. You can derive it. Everything here is a coordinate free. Well, you can derive it using some coordinate to find this this formula, or you can even just think about physics to find this formula. So this, but you can think about this as a linear function of the force. So you can linear mapping of the force, spatial force. So it has a matrix representation. So typically we write, or equivalently, so we will have the cross star matrix representation is nothing but, if you think about this, is omega skew symmetric. Here is V skew symmetric 0 and omega skew symmetric. Okay, so V cross star F almost like a 6x6 matrix times this F give you another vector. Okay, that's similar to the spatial cross product for twist. Okay, that's the definition, and then we will have, based on this, because each vector is multiplied by the same thing. Based on this, these are side note. Okay. Based on this, we'll have xb star dot actually equal to, because each vector is the same. This v cross star xb star. Okay. Now let me think about this as this way. Okay. It's a matrix. This 6x6 matrix times 6x6 matrix give you another 6x6 matrix. Quantify the change of that coordinate basis vector. Okay. Anyway, so overall, also there's a fact. Let me just using another. This is a fact. You can check very easily. V cross for force star equals to V cross without the star, that's for velocity, spatial cross product, transpose, and negative. So they are related by, you just take a transpose and then take a negative sign. Because this symmetric matrix, if you take transpose, you always have a negative sign. Then you just factor that negative sign out, you get the spatial transform, spatial cross product for force. Okay. So then in coordinate free way, we can write, you can, in your mind, you can think about this. So F dot, okay. Let me use this black color. So F dot actually equal to XB star FB ring, that's the actually the what apparent derivative of the coordinate, plus XB star dot, right, which will be V of B cross the thing times XB star times FB as well. Okay, so that's almost like a coordinate-free way of representing the change of force. Then you need to derive it. You can express this physics using different coordinate system. For example, you can use A or B or C or O. Okay, those are background knowledge, and in case I think everyone should have all the information or general direction to think about this if you want to truly understand every single details. Okay, but if you don't want, you can just memorize if you want. But I encourage you to think, especially PhD student, you need to really understand what's going on here. Okay, so suppose, I mean, these are general formula. Suppose a frame A is moving with velocity VA of A, and I think this is VA of A, so the frame A is moving, right? And so if I want to say express this change of frame with, change of the force, this is dot, this D of F dt means coordinate free. It's just a vector change, okay? Change of that vector, it gives you another vector, force vector, and you represent that force vector in A frame, okay? And this equals to, this is a parent, this is a parent, right? This is F a ring, which is a parent derivative, and plus something due to the frame A is changing, the coordinate of that A is changing. It's just because of this part. Okay, so you have VA expressed in A cross star times FA. Okay, if you want to represent this guy in B, then it becomes identity. All right, so that's why. So that's why this FA, there's nothing like they have this guy. Then hold on, this is the similar. So momentum has the same property as force for change of coordinate, for also for this kind of spatial product. Okay. I know it will be for some students it will take some time for you to truly get to there. Okay. Now let's reach the final step. Okay. All we are trying to do here is trying to really give you all the details so that you can have just one elegant formula for single rigid body dynamics. And if you know this well, then all the others rigid body dynamics will become easier, okay? And here it's just this. What physics says is change of momentum equal to the total net external wrench. Okay, this is the net external wrench applied. All of them will contribute to the change of the spatial momentum. All right, and this is physics. That's fine. But the particular formula, this guy, is a really nice formula. You don't need to memorize different formula for different frames. This is a coordinate-free representation of this physics. Okay. So what do I really mean by that is I can write a little bit. So for example, if I choose a coordinate, let's say B, IB times special acceleration plus VB cross star, there's a star, this is a motion vector cross, okay? Force, special cross product for forces, and times I of B, V of B. Okay, so I can choose A or B. This B can be arbitrary. They will have exactly the same formula, okay? When you do other kind of derivations, for other approach, oftentimes you need to have very, very ugly looking kind of equations. And this is true actually even when B is away from central mass, COM, okay? Or it's moving at other velocity. Either way is fine. Okay. Let me ask maybe Hongbo.
Yeah, here.
What is the velocity? What is V here of B? The velocity of what?
The velocity of the body fixed point the current.
Well, this is the special velocity. Okay, this is
yeah.
This is the body. Okay, this is the body. And there's a force, there's the external wrench, right? And here is the center of mass. This is center of mass. Okay, so this guy is the velocity of the body or a frame B of the velocity. This is the B, let's say. Let's even make it more interesting. Okay, let's say this is the here maybe it's my B frame. Okay, my B frame can even represent the inertial frame. That's fine. So body is moving, right? A B may or may not moving. So but anyway, so VB, what's the physical meaning of this? It's the velocity of what expressed in B? Is it velocity of B or velocity of body? Maybe it's hard to know from what I said so far. It's velocity of the body. Okay, this V is the rigid body velocity. Acceleration is rigid body acceleration. Okay, it has nothing to do with what frame you consider to express this velocity or rigid body. Okay, so all this V means the same thing, the velocity of the rigid body. Okay, and it's only rigid body has the inertia, has all these things. Okay, this velocity of that. Okay, and this guy have this cross, this kind of cross star has nothing to do with coordinate system is moving. It's really kind of inertia is changing. That's because of that. Okay, well, let's maybe after we derive that, it will be a little bit. I don't think it will completely clear, but at least it will be better. So if I think about this, if I want to think about this as d dt, this is coordinate free expressed in B, okay, equal to d dt h coordinate free expressed in B, and of course it's coordinate free expressed B. This is d dt. We know h is IV, right? That's the spatial momentum. Then you get let's say that. This is in B. You got IA, of course, derivative of the spatial velocities. This is fine, right? And then plus I dot V, right? So overall, we will have IA plus V cross I V star. And this card, so this guy, because this term is here, because the external force is used to do what? It's actually this term actually due to speed or V or velocity is changing, so that you have acceleration, right? It's changing. This term, why we have this term is because this is really accounts for the fact that inertia is moving. Inertia is moving. So the inertia is changing over time. That contribute to this part.
Professor, there is a typo in the beginning of the function.
Where?
B d over dt f. The beginning of the function.
D dt. You mean what? D dt?
There is no d dt. It should be.
Oh, okay. Sorry. Yeah. You're right. Sorry. There's no dt. So it's a change of spatial momentum. Sorry. Okay. Great. Force doesn't change. The external force applied to the body cause momentum to change. Okay. I think how many time I have? So let's briefly discuss how this we can let me do this. Okay, let's work. Why this is the case? Let's work with the inertial frame. To derive the equation. Okay. To derive the Newton-Euler equation. I'm not sure whether we derived it before, but let's do it as an exercise for all the spatial algebra we introduced so far. Okay, that would take some effort. Hopefully we can finish. I don't think so, by the way. This is our body. Let's now do a special assignment. Let's say if the body, a B frame is attached to the body. Okay, this is a force external. This is the body. Okay, this is our inertial frame, which doesn't change. Okay, this guy has a motion, which is a V of the body. Okay, that's the rigid body. So let's assume frame B attached to the body. Now, during the derivation, let's assume that, okay? Attached to the body. What does this mean? B is part of the rigid body. It moves exactly the same way as the rigid body. That means V of B equal to V of the body because they are the same body now, okay? I hope you can get that part. So, in this case, this implies that, okay? Also, in this case, I of B, the spatial inertial matrix is constant because the B is rigidly attached to the body. So if you do the integral of to define this inertial matrix, you find it out. It doesn't really change over time anymore. It only depends on the geometry of the body. Okay, these are the two facts after we do this. Okay, but when we derive things, let's say we work with, let's work with inertial frame, right? So overall, we will have d dt. We need to find out what it is. This, right? The spatial momentum expressed in O frame. Okay, so that's d of dt, I in O and the V in O. Okay, I hope. So Fuzhen, correct me if I have any typos or anything goes wrong. Okay, d and dt. I have term like first of all, let's say first term is I dot 0 V of 0 plus I 0 times acceleration in 0. Do you agree, Fuzhen? Why is the case?
Yes.
Because we work in inertial frame. The inertial frame here, the parent derivative of V will give me this thing, right? Okay, I hope that's fine. So all we need to find out is this term. What is it? Okay, so let's and I know. Let's make it clear. I know it is this guy may be changing over time. Okay, I-O may be changing. Only I-B, the B is rigidly attached to the body, does not say it's a constant. It only relates to the geometry and mass distribution of the body. And then I can derive it. So for example, I would say I need to relate that to something doesn't change, right? So we'll have a, let's see that d dt, this term will be, let's do the change of coordinate for inertial matrix, which will be B-O star I-B, okay? And times X-O-B, that's my here, and V of O, no V of O, sorry, times V of O plus I of O, A of O. Now this term, I know this guy doesn't change, right? I have two matrices in pre and after multiply this matrix, so both of them are time dependent, so I need to take derivative. Roughly speaking, I will have xbo star derivative, okay, times ib xob bo plus, then I hold the other part fixed and then take derivative with respect to another time invariant case, which is xbo star ib xob dot, okay, and times vo and plus this guy. Okay. Then I need to ask Fuzhen, do you remember what is this again?
This is v spatial velocity b times
this
star.
Okay. Yes.
X b star.
Sorry, I'm ahead of you. Anyway, times xbo star. The derivative is disappeared, then you need to multiply by that. Okay. That's what we just introduced. Okay. If you are not comfortable, just review that or think about it out. For now, let's just take it for a fact. Then this is IB and OB V of O. All right, that's where how did we handle this derivative? Then we handle this derivative. Okay, that's actually BO star IB. This derivative. It's a little bit tricky. Let me do a note. Okay, here. What we know is x bo star dot without star dot is VBO cross XBO. That's what we got before, right? But now here is OB dot. You cannot, the formula doesn't hold anymore. You have to work directly. So you need to know the fact is that XBO times XOB is identity. Okay, it's 6-dimensional identity. So if you take derivative, so that means XBO dot times XOB plus XBO times XOB dot equal to 0. All right, and then what we want is this term. What we want is this term, OB dot. So overall, we will have, let's do that. So that I can have XOB dot equal to negative. This guy moved to the right, and so I have a negative sign. Then I pre-multiply by OB, XOB times this guy, okay, times XBO dot times what? XOB, okay? And I know this guy, XBO dot, I know what it is. So it's negative XOB times X, that's V of BO cross, times XBO times XOB, so disappear. So overall, we will have, I'm a little bit fast, sorry, this. XOB dot equals to XOB negative, and multiply this spatial cross product matrix, but from the right. Okay, Fuzhen, this is okay so far?
Yes.
Okay, so you know how we can get this, but these are technical details. I just want to tell you this is the case. Then what we got is let's plug in this guy. We will have a negative sign. Let's do the negative sign here. Sorry. So we will have negative sign here, and XOB, right, times VBO cross. Yes, and that's that's this dot, and then then I times VO, then I plug plus IO AO. Okay, so overall we will have what is it? This guy is VB0 cross spatial force cross product times this. This actually is what? This is IO, right? They change coordinate to IO times VO. That's the term simplified to this. And this term, you find it out. VBO, VB cross, actually this is also V of B. The V of body equal to V of B. So this guy, this is also V of O is V of B. As I mentioned before, V of the body, that's our V, by the way, is just V of the frame. So they are rigidly attached to each other. So spatial cross product actually has the same property as the R3 cross product. Is a vector cross itself will be 0 because it's defined. You can think about this. Okay, vector cross itself will always be 0. Then this guy disappear. Okay, this is 0. So what we have is plus IO inertia O. Okay, that's our here. Okay, that's the result. So overall, we will have, if I reorganize it, IO inertia acceleration plus VB cross star O IO VO. Okay, that's our Newton-Euler equation. Okay. If you change this O to any other frame, you can derive again. You can find it's exactly the same. So no matter what the frame you choose, you always have this form. So this form is actually coordinate free. Okay? If you learn from other type of things, I don't think you can have a very unique. This really kind of tell you the underlying nature of the problem. Okay, two-part spatial acceleration and also another cross part that is due to inertia is changing. Okay, that also cause forces.